So in the numerator, we want to factor. You've got a 0.4 and a 10. Let's factor out the common 0.4. So taking out the 0.4, and when you take it out, you're dividing it out. So 0.4 divided by 0.4 leaves you with 1x squared. And then 10 divided by 0.4 is 25. This, take yourself all the way back to algebra, is the difference of squares. So that also factors. So I'm going to come over here and run out of room. We got the 0.4. That will factor into x and x gives me the x squared. The two numbers multiplied together to give you a negative 25 that add up to the 0, a minus 5 and a plus 5. There's the numerator completely factored, the three factors. The denominator is x minus 5. You can cancel those out, and you're left with 0.4 times x minus 5. Okay, so why did I do all that business? All to help me find the limit. So I want to know, is there a limit as x approaches 5 of f of x? Well, if we have the graph, we can look at it. The graph, yes, we already decided my fingers are getting closer and closer to 4. We saw it on the graph, we saw it on the table. Algebraically, I should be able to get the same answer without the graph. And the way we do that is you remove the discontinuity, and then all you want to know is what's the function value at that value you're trying to approach, the 5. When I'm putting it into the reduced, I guess, version of f of x, after we remove the discontinuity, so it's 0.4 times 5 minus plus. Oh, look at there, I made a mistake already. 5 plus 5. 5 plus 5 was the factor left over, not, excuse me, x plus 5 was the factor left over, not x minus 5. So you got 10 times 0.4 for an answer of 4. So we got the limit. This is algebraically showing the factoring and canceling, plugging in, and this was just looking at the graph and getting it. Did all that business. Now, what I want to do is the second, oh, well, not the second, yeah. I want to make this graph just a little bit stretched out, a little bit bigger in scale. Put that hole at 5, 4. Oops, sorry about that again. I gotta pay attention. Put the hole, I made my axes a little bit bigger than I did up there because I want to add to this graph a little bit. It is crossing just so I can make a nice line. 0, 2. So here's my question. To keep f of x within 0.01 units of 4, how close must x be kept to 5? So, what that question is asking, and I'm going to exaggerate the 0.01, because 0.01 is not very far. Let's just say I want to stay within 0.01 units of 4. So let's just, I know this is bigger than it needs to be, should be, but if that's 4.01, and if I go 0.01 before the 4, I'm at 3.99. We will see that there's a little window around the 5. And now if we read down from those intersections, best job there. But I want to know how close to 5 do I have to stay in order to stay within this 0.01 units away from the limit. Okay, that's our goal. So what we're going to do is use algebra to figure that out. And we already set up the window. I want the function to stay between 3.99 and 4.01. So I'm going to set up a triple inequality. 3.99 is on the smaller end. I want the function to stay in between that and 4.01. I want to know what x value makes that happen. So all I need to do now is substitute the equation in here. So 3.99. In place of f of x, I'm going to put in that reduced equation, the one after we factored out the x minus 5. So 0.4 times x plus 5 is less than 4.01. So now we just have to solve for x. A couple different things you could do. You could distribute the 0.4 right now and then do the algebra, or you can just divide everything by 0.4 right now to get rid of it. So the 3.99 divided by the 0.4 is 9.975. X plus 5 is left in the middle. .025. And I'll subtract 5 from everything. So I've got 4.975 is less than x is less than 5.025. So if you look, what we just found were the two x values where my dotted lines came down. This one is at 5.025. This one is at 4.975. But those two are not the answers to my question. The question said, how close must x be kept? So how far away can I be? Well, I need this distance here. And it's 0.025 away. So I need to stay within 0.025 units of the 5. So now that we did all of this, I'm going to give you the formal definition of limit. This is the definition that will be on your chapter test in a few days. So here we go. Definition of limit. L is the limit of f of x as x approaches c but never equals c. If and only if for any positive number epsilon no matter how small, there is a positive number delta. Such that if x is within delta units of c, then f of x is within epsilon units of L. So, there's 4 key values in here. The limit, the x value that you're approaching, c, the delta, nice lowercase Greek delta, kind of looks like a d, and then epsilon is an e. You need to be able to go back to the problem we just finished and tell me those 4 key values. So if we look back, geez, was that on the screen? I didn't even look. I'll leave it there in case it wasn't. Sorry again, I'll get better at this. Okay, but we do want to find the 4 key values in this problem. Okay, well, the number we were approaching was the c value. Let's see, so to keep f of x within 0.01 units of 4, how close must x be kept to 5? So we were approaching that 5, so the 5 is your c value. And the c value is always going to be your x value. L is the limit, that's always your y value. That was 4. The epsilon is how close to the limit. How close to the limit did we want to stay in this problem? We wanted to stay within 0.01. So the epsilon will be that distance on the y-axis. And then delta was how close to our x value that we were approaching, how close to c. And that was our 0.025. So that's the distance on the x-axis. And what's kind of nice is everything's in alphabetical order. You know the x-axis, y-axis. C and L. C comes before L, so C is on the x, L is on the y. Epsilon and delta. Delta, obviously D comes before E in the alphabet, so D is your distance on the x and E is your distance on the y. So those are kind of easy to pair up. And that, I believe, is it.